Okay, let's get started. Did you have a good Halloween? No. Well, you play bingo. My wife keeps on telling me to take her to play bingo.
It's fun. She's so bad.
Yeah, I haven't done that yet.
It's fun. Don't do it.
Don't do it. All right. All right, well, let's get down to business, all right? All ready? Still have a table. They all have their names out still. They all have their names out. That's awesome. That's like a bonus points or something. I'm not good with names. I had a good Halloween. I don't remember much of anything. Okay. One-to-one functions, 6.2. This is the only thing we're covering today. All right. This concept comes into play a lot later on, especially in pre-cal and in calculus. This general concept of having a one-to-one function and therefore what's called an inverse function. So remember last time, it was a long time ago, right? It was a week ago that we met. And we were talking about, what's that? It was a week ago. Extra 10 points, here we go. I keep on forgetting to turn the volume off.
I don't even need to take the final. I can do it 50 on the final.
Okay, so we were talking about functional composition last time and how you can put two functions together. You put one function inside the other one, right? And we had these things like this. Remember that?
Yeah, fog and golf.
Fog and golf and FOF and all that. So we're going to use that today when we're talking about what are called one-to-one functions. So first recall that in order to be a function, you have basically one input goes to one output. That's what it means for something to be a function. You have to be able to take one thing when you plug it in, get one thing out. And if we look at that in terms of a picture, if we're going to call something a function f, then if I have an input here, which is a number, it's got to go to one place. So that would be a function, yes? Would this still be a function? Hold on. I'll put in front of this for every, I'll change that single, all right? I'm changing the wording a little bit. For every single input, it goes to one output. Yes. That still works? Yes. Even though they go to the same place? Yes, that's still a function. That's what we do when it's graphical, which I'll show in a second also. Yes. If it were graphed, that's what we'll do. All right. But this picture, each single input goes to one place. Doesn't matter if it's the same place, just as long as this doesn't happen. Right? If that happens, that's not a function. Because you have a single input that goes to two outputs, right? Okay. Now, for a function to have an inverse, and we're going to get into talking about what an inverse means. It must be what we call, quote, one-to-one. So what one-to-one means is not only for every single input do you have a single output, but each output is unique. So you cannot have two numbers going to the same place like we did before. That can't happen. So we say for each input, there is a unique output. Cubic would be an example of one. So let's take a look at the picture of this. One input goes here. So it's a function, yes? And it also, so far, appears to be one-to-one because each input is going to a specific output. Here to here, like that. Here to here, something like that. That would be a one-to-one function. You cannot have this happen. That can't happen, right? Because now this output is not unique. It actually, there's two places in the domain that get spit out to the same output, so that's not a unique output. Make sense? Yes? Okay. All right. So if you have a function that is one-to-one, then that function has what's called an inverse. And the way we look at an inverse, well, when you think about inverse, what do you think? Opposite, something like that? The inverse of a function is another function that undoes the original function. So let's just look at an example. All right, I'm going to give you two functions up here, and I want you to notice that they have a property to them. So as an example, let's look at the function f of x equals 2x plus 1. Okay, we all know that that's a line, right? We could graph this, I hope. It's been a while since we've graphed lines, but if I were to graph it, I would start probably at my y-intercept, which would be 1. Say that's 1. And then to get to another point on this line, I would use the slope, which is 2, right? I go, what, slope is 2 over 1. I go up 2 over 1. So up 2, and then over 1. That put me here, and I draw this line, like this. Now, let's check to see if this is a function first. So visually, the fact that I wrote f should make you, is there a ruler around here? Do y'all see that ruler? The big meter stick? Is it laying over there? Is that it? There we go. Thank you, sir. What'd you do over here, man? Okay, so when we look at this, to check to see if this is a function, we use something called the vertical line test. Show of hands, how many of you remember the vertical line test? Yeah? All I'm doing is drawing vertical lines, making sure I don't hit the graph more than what? More than one time, which wouldn't happen here, right? Now, to see if it's one-to-one, we actually do the horizontal line test, which is the same test, but with horizontal lines instead. So to see if it's a one-to-one, we use the horizontal line test. So let's do this. If I draw horizontal lines, do I ever hit the graph more than once? No. So this would pass both the vertical and horizontal line test, wouldn't it? This would pass, check mark, it passes, okay? It passed the horizontal line test. Therefore, it is a one-to-one function also, which means that it must have an inverse. There must be some function out there that basically undoes this function. All right? Let's take a look at it. And I'm going to write it up here, and then we'll check it, okay? I'm going to define a function up here. I want to define a new function, g of x. And I'm going to tell you that it's x minus 1 over 2. Now, we'll actually figure out how you would get that in a little while, but for now, just take it on faith that comes from somewhere, all right? Don't worry about where it comes from yet. So let's take a look at what happens, all right? If I take a number, I'm going to draw a picture again. If I take a number and I plug it into f, right? So let's take the number, how about 0? We can plug 0 into this, right? If I take the number 0, where does it get mapped? Mapped is another word for graphed. Okay, where does it get mapped? 0 gets plugged into this function, it spits out what? 1. Well, guess what? If we take 1 and we plug it into this function, where does it go? 1 minus 1 is 0. 0 over 2 is 0. So guess what? There's a way that I can send the 1 back to where it came from using the g function. You see that? And I can do that for any number. It should work. So what happens if we plug 1 into the f function? 1 gets sent where? To 3. And let's see where 3 gets sent in this one. 3 minus 1 is 2. 2 over 2 is 1. So it gets sent back, doesn't it? By g. Understand? We are guaranteed that if we start with the function and it is 1 to 1, we're guaranteed that we should be able to find an inverse function for it. And that inverse function will undo what the original one does. All right? Now do you see why it has to be 1 to 1 though? Think about if you had a function that was not 1 to 1. So let's say you had this going here and you had another one going here. What problem would I have when I try and go backwards? Where do I send it? It came from 2 different places, right? So where does it go back to? You can't do it. You can't say both because then it wouldn't be a function in that direction. So both f and g have to still be functions. So the only way to make that happen is to make it 1 to 1. All right? I hope this all makes sense. Visually, you kind of get the idea? All right. So what I'm going to do now is I'm going to draw a couple of pictures, and I want you to tell me on these whether or not these are functions and whether or not they're 1 to 1. All right? So for these examples, question is this a function? Is it 1 to 1? Another question I could ask here, instead of is it 1 to 1, I could ask you, does it have what? An inverse. Those two questions are synonymous. They basically mean the same thing. All right, so here are a couple of pictures for you. First one. How about your classical parabola there? Is a parabola a function?
Yes.
Yes, it is a function. F, check. It's a function. It is not 1 to 1 because it fails the horizontal line test, doesn't it? If I draw a line right, let's say there, I'm going to hit it twice. And so it would fail. So for 1 to 1, I'm going to write 1-1 for 1 to 1. And no. All right? Is there a way that you could make this a 1 to 1 function? What would you have to do to make that 1 to 1? That's a little more, because then it wouldn't really be x squared anymore, right? I want to still make this x squared without, that would be y squared. So that's a different.
Give it a domain or something?
There you go. If you cut the domain or you restrict the domain. So how about I do this? This right here, does everyone agree, was just the function f of x equals x squared? Yeah? What if I said instead of that, draw me f of x equals x squared, but the domain, I'm going to restrict it. I want you to only draw it between 0 and infinity. So I'm coming in here and physically putting restrictions on the drawing myself. Then if you draw this, you are only allowed to plug in 0 and then positive numbers. And therefore the picture would look like this. Wouldn't it? Is that a function? Yes. Is it 1 to 1? Yes. That we should be able to find an inverse for. Only if we restrict that domain, though. All right? That's going to come up in pre-cal. And I know some of you have already seen like the sine and cosine functions in high school perhaps. But, you know, this is beyond this class, but in pre-cal you study these sine waves. And these are all functions. A sine wave is a function, but it fails to have an inverse because it fails a horizontal line test. So what we do is we restrict it. And we cut it off in a certain way. We actually do it like that for sine. We cut it off like that so that just on this little piece of it, it's a function, it's one-to-one. So this domain restriction is something that comes up later. Okay. Everyone understand that? Let me give you another one. I think, Lily, you said cubic, right? Function? X cubed. X cubed looks like this. That's f of x equals x cubed. Is that a function? Passes the vertical line test. Horizontal line test? Pass. So this would be a function and it would be one-to-one. Sure, if you want. If you prefer that, yeah. You can write this. You can write. As long as we're getting the idea across, right? All right, next.
Is that chocolate milk?
Why? What's wrong?
Is it?
No, it's not chocolate milk. Chocolate milk. What's the deal? I'm not acting strange up here, am I? I've never tried.
Remember 2 Wednesdays ago? Remember 2 Wednesdays ago? Dude, you're so
All right. Most students have no problem with the graphical ones, all right? Let me give you one more and let's see if you can handle this. This is actually the graph of y, x equals y squared. Is this a function? No. Fails a vertical line test. Is it one-to-one? Horizontal line test? It is not one-to-one. Because it's not a function to start with. So there's a little bit of an issue we have to deal with here. That's right. That's right. So you can't, to find the to be able to, you say that a function is one-to-one, right?
Yeah.
But if it's not a function, you can't say it's one-to-one. So the condition to be one-to-one is that you first have a function to start with, or else you can't. So this actually doesn't make any sense. So you don't just want to be focusing on the test itself. You have to do it in the proper order. Must pass vertical line test first, then you can apply the horizontal line test. All right? Now you'll learn later on, like in my Cal 1 class, no, my Cal 2 class, right, you know, everything that we've done in this class, we always treat x is what we call the independent variable. That's the domain variable. We plug x's in here, and then the y's are what come out, right? And so our function always went from here to here. And so in order to test it, all we did was, to test if it was a function, all we did was vertical line test, right? That's all. But you can also treat y as the independent variable and x as the dependent variable and be looking at it the other way, where you plug in y's and it spits out x's. And if you did it this way, this would actually be a function of y. It would be, but everything's sideways. It's beyond what we want to do in here right now, okay? But just, there's some language in here with this. When we say is it a function, we're assuming that x is the input variable and that y is the output variable. All right. So I hope you have some general visual idea of what it means for a function to be one-to-one. I've shown you an example, kind of a function and its inverse. Now what I'd like to do is define, using the mathematical definition of what an inverse of a function is, all right? So if f is a function, right? So we have to have that to start with. If f is a function, then I forgot to put and it is 1-to-1. And it is 1. What's wrong? You don't like that I write in all caps? Okay. If f is a function and it is 1-to-1, then it will have an inverse, right? What? What's wrong with y'all? I've been writing like this all semester. What's wrong? What? Is there something wrong with the way I write? Oh, okay.
I honestly noticed that.
No, I learned cursive when I was younger, and you know, it was all right. But
That's why he writes in all capital letters.
I write in all caps. I print when I write. That's the way I write.
Look at y'all making me feel all self-conscious.
I'm not self-conscious. I'm curious why it's such a big deal now, and we've been here for like what? How many weeks? 9 weeks. Oh, I get it. All caps is like in texting. It's like screaming. Ah, okay, I get it. Sorry.
Function.
It's a generational thing here. Sorry, it's a generational thing. No, this doesn't mean like it's a function here. You know, like that's not what I mean here. All right, so if f is a function and it is 1-to-1, then it will have an inverse, right? Further, we will denote it with the following notation. F with the little -1 up there. That's what we will call the inverse function. Remember that when we name functions, f of x, g of x, h of x, c of x, this thing out here is the name of the function. So this is the f function, the g function, the h function, the c function. You could even have something like the cost function, then the name of that would be the cost function, right? So this thing out here is just the name of it. So we will use this as the name of the inverse function to let everyone know that this function undoes that one, okay? If you had another function like g and it had an inverse, you would go and call its inverse g inverse like that, all right? I think that's good. Now, I'm going to continue this note, but I want to write up on top here. To check that f and f inverse are truly inverses, we must have the following. There's only one true way to check to see if two functions are really inverses of each other. There's only one way to do it, and here it is. First, if you take f and you compose it, like fog, goth, right? If you compose it with its inverse, so this is like f of g of x, then when you do that, you should get what out? So let's think about this, all right? Okay, here's x, right? I plug it in, it comes out to be something, right? The inverse is going to take it back where? Back to x. So this says if you take something, doesn't matter what it is, you plug it in and then plug it into the other one, at the end of the day it comes out totally unchanged, right? But that composition has to work both ways. So not only does this have to be true, it has to work when your composition is flipped over. Okay? That's how you check to see if two functions are inverses. So let's go ahead and do that. Let's do a problem where we have to verify it. How about the one that I gave you earlier? It was 2x plus 1. The other one was x minus 1 over 2, right? Let's check that those were inverses. So as an example here, are these inverses? So I'm going to give you the function f of x equals 2x plus 1, and the other function g of x was x minus 1 over 2. Those were the two functions we had. I want to see if these are inverses. They look like they were, right? Because we had checked, if you go back and look, if you're writing your notes down, we had checked that when you plugged in 0, it spit out 1, and then 1 went back to 0. When we plugged in 1, it spit out 3, and then 3 went back to 1, right? But just because it happens twice, does that mean it's going to continue to happen forever? No. I mean, it's a good sign, but it's definitely not a precise way of proving something, right? Right? Just because the sun keeps coming up, does that mean the sun's going to come up tomorrow?
Yes.
No?
Something.
We won't get into it, but just because something happens millions and millions of times in a row does not guarantee it's going to happen again. So how do we check it? So what do I want to show? What do I want to show? There's two things. Nope, we're not going to do graphs. This has to be done algebraically. Okay, so I have to show that when the two are put together with composition one way, it spits out x, and when they're put together the other way, it spits out x. So I want to show, and we like to say this a lot in mathematics, especially as you move on and do more math. We always say, want to show. You're trying to explain to whoever's reading your work what it is you're trying to do. So we write WTS instead. It's just a shorthand for want to show. I want to show the following two things. One, f of g of x must be what? X. And the other composition, g of f of x, must be x. I have to show those two things. Okay? If I show those two things, I'm done. I've shown that they are inverses, right? You buy that? Okay. So let's do this. May I erase? Yeah. All right, so let's do the first one. Let's write down what f of g of x is. And we did this last class, didn't we? You do f, inside goes g, right? Which is f, and then inside of f, replace the g of x with whatever g of x is. In this problem, it's what? X minus 1 over 2. And so now you're going to take x minus 1 over 2, and you're going to plug it into the f function. So it's going to go into this function and replace the x right there. Isn't it?
Yes.
Okay. So it's going to go 2, that's this. But instead of x, this whole thing, I'll put it in parentheses. What's still out here? Plus 1. So that is the f function, 2x plus 1. But instead of x, all of that. Y'all see what happens here?
You get it.
The 2's cancel, right? Because this is multiplication. That's like 2 over 1. That 2's on the top, this 2's on the bottom, so they cancel. All you're left with was x minus 1 and then plus 1. So x minus 1 plus 1 is x. One of the two things we've shown. Now you have to show the composition the other way. Okay? The good news is when you do this on the test, when you verify that two functions are inverses, you'll know if you're getting the right answer because you should be getting x here. If you don't get x here, something's messed up. All right, so let's do the other composition. The other composition I have to show is that g of f of x must be x. So that's g with f plugged in, which is g with 2x plus 1 plugged in. And if you look at your g function, we're going to replace that top left x, right? The g function is x minus 1 over 2. We're going to replace that top left x with all that. So it's going to be 2x plus 1, then minus 1, then over 2. Now I put the parentheses just to stress that this got plugged in for this, but I didn't need the parentheses because there's no negative out here, nothing gets distributed through. So we get, let's see, 2x plus 1 minus 1 over 2. You do everything up top first, right? Do everything up top first. Get your 1's to go away. You get 2x over 2. 2 over 2 is 1. 1 times x is x. Done. All right? You verify that they are inverses. Okay? Now let's do one that's a little more complicated. I keep on saying is, are these inverses? F of x equals x squared, g of x equals square root of x. Let's try and do this without anything other than checking the two things. Right? There are two things we have to check. But we should already be thinking we had a problem with this earlier, didn't we? The x squared we said didn't have an inverse because it wasn't 1 to 1, right? Let's see if we run into that issue at all when we try and check this. With keeping in the back of our mind that we know we should have a problem here. Well, let's see what happens. Let's see. If we do fog, it's f with g inside, right? And that's f with g, which is square root of x. Remember, I'm trying to show those two things, right? And when I take the square root of x and plug it in here, I square it, and I should just get x, right? Okay. So that wasn't a problem. 2, if I try it the other way, it's g with f plugged in, right? Which is g with x squared plugged in, which is the square root of x squared, which would be x also. So we're done. I mean, we verified it. So it doesn't seem like we ran into any issues here, did we? Okay, so this is what I said, we have to be careful, right? You have to go back and you have to think about what's happening here, all right? Do you remember when we were doing domains of composition? We did it last class. Let's take a look at the domain of this first one, okay? Let's look at fog. What's the domain of this? All right, so how did we do domain when we did the f of g of x? Remember, I first wrote down x. I said x is going to go through which function first? G, and then that's going to come out g of x, and that's going to go through f, right? And come out f of g of x, whatever that is. That look familiar? Okay, so when you take x and you go through g, g is the square root function. And then when you plug that through, what happens when you do all that? It spits out just what? X. But what's the restriction going from here to here? X had to be non-negative, 0 or bigger, right? The restriction here is that we can't take the square root of a negative number. So the restriction right here so far is that we must be on the interval 0 to infinity. Agreed? And that's from this step to this step. Now once that number comes out, it doesn't matter what it is, because what am I going to do with it? What does f do? Squares? You can square any number, right? There's no issues? So the only restriction I have is this one, right? That's the domain of this. How about the next one? Is there a domain restriction here? So look at domain for this one. I'll draw this thing again, but I'll erase this one. This one, x goes through f, comes out x squared, comes out x, doesn't it? Is there a restriction going from here to here? No, because you can square any number. That's no big deal. But remember, g is square root, isn't it? We need to make sure that whatever we're sending through, it just can't be negative, can it? Can't be negative? But it wouldn't matter, right? Because it's being squared, so by the time it gets here, it's already at least positive. It could be 0. So there should be no problems going from here to here. Understand? So there's all real numbers, negative infinity to infinity. This is the domain of f of g of x. This is the domain of g of f of x. Yeah? But for inverses to exist, you're looking at the full loop, aren't you? You're looking at both directions together. So our domain has to be both of these combined. And if this is saying everything, and this is saying, oh no, only from 0 to infinity, then 0 to infinity can be your only, it has to be your restriction. Because this one is too much, got it? So overall, you can say for sure that f of x equals x squared and g of x equals square root of x are inverses if, x is an element of 0 infinity. As long as the x's we're using are from here, we're okay. Understand?
So we have to do that every time, then we have to check it.
I would always look at the functions and see if you can tell real quick what the graph is, whether or not there's a domain restriction. But you can tell when you're doing the composition, you can tell if you're going to have a problem. If you see square roots or you see fractions where your x is in the bottom, you'll have to pay attention to it. I'll do another one so we can see how it works. So could I do this then? Could I then say, all right, I could call this, yes? Would that be legitimate for me to replace g of x and call it this instead?
Yes.
And that would tell everyone, look, this function and this function are inverses. So it's already been checked. I checked it. You don't have to check it. This is the inverse of this. As long as this is true, that works. Okay? Now, I hope this satisfies the fact that when we drew x squared, we said we could only draw one side, right? So do you see that this right here takes care of that? If I'm only allowed to draw from 0 to infinity, then I'm only going to draw that. And then the inverse function, square root of x, remember what square root of x looks like? It looks like this, right? They both have the exact same domains in these two pictures. That's a one-to-one function, right? This is a one-to-one function. So, good?
So on the test, that would be the answer we come up with?
If I said verify these are inverses and find the domain, then you would need to do that, yeah.
So it has to be expressed as, like I said, it's not gonna be like, hey, and then trick me out and like.
Yeah, no, I will. What I want you, mostly on the test, when I say verify that these are inverses, what I want you to be able to do is show that f of g of x is x and g of f of x is x. I'm not going to be stressing the domain part. In the homework, I'm going to ask you to try. But you know, if you get hung up on it, you get hung up. Let me do another one, okay? That way you can see something else. Are these inverses? F of x equals 2x plus 3 over x plus 4. And then g of x equals 4x minus 3 over 2 minus x. All right, this is a more challenging problem, all right? Do these functions undo each other? And let's do find domain. So do you want to go and do the domain first, or do you want to do the domain after we're done checking? After? Okay, let's check it first. So what is it that we want to show? We want to show, 1, that f of g of x equals x, and 2, that g of f of x equals x. Those are the two things we want. Every time I ask you to, if two functions are inverses, you have to check these two things. Let's try the first one. So for 1, f of g of x means f with g plugged in. Can I just go ahead and plug g in right now instead of having to write g of x? Can I just write this? It's okay? 4x minus 3 over 2 minus x. That g function is getting plugged into this f function. And that's going to suck, isn't it? Because we've got to replace this x right here and this x right here with this big rational expression. Let's see what happens. This is going to become equal to 4, and then in parentheses what? Oh, wait, sorry, not 4, 2. 2 in parentheses something plus 3 over something in parentheses plus 4. Do y'all see how I'm setting this up? This is the f function. But into it, I'm plugging in the g instead of x. So here comes g in here, 4x minus 3 over 2 minus x. And down here, 4x minus 3 over 2 minus x. Now that's not as nice as the previous two, right? Previous two, the algebra was really simple. This is going to test your ability to simplify complex fractions. So what I'm going to choose to do here, and there's different ways of doing this. This is just what I'm going to choose. I'm going to take this 2, which is really like a 2 over 1, and I'm going to distribute the 2 through the top to make that an 8x minus 6. And then I can drop the parentheses. Down here, I can just drop the parentheses right now. So I'm now sitting here looking at 8x minus 6, the 2, through the numerator only. Then plus 3, and then over 4x minus 3 over 2 minus x plus 4. What should I do now? If you have complex fractions, get common denominators. So look up on the numerator here. This is like a 3 over 1 right here. I'm going to get a common denominator between these two of 2 minus x, which means I have to multiply the top and bottom here by 2 minus x over 2 minus x. I will do the same exact thing in the denominator to get a common. So this will be 4 over 1, so I multiply top by 2 minus x, 2 minus x. Do you all understand what I'm doing? Trying to get a common? So we get 8x minus 6 over 2 minus x plus. Now distribute the 3 through the top. 6 minus 3x. Yes? Over 2 minus x. And then on the bottom, 4x minus 3 over 2 minus x plus 8 minus 4x over 2 minus x. So again, distributing the 4 through there. Now the top and bottom both have common denominators, so we can put them together. So when we put these two up top together, we do 8x minus 6 plus 6 minus 3x, which I believe is just 5x. I'm going to write it all out just so everyone sees it. I'm putting the bottom two together also. So the top here is 5x over 2 minus x, and the bottom is 5 over 2 minus x. And when you have a fraction divided by a fraction, it's the same as multiplication flipped up. So I can say, forget the division, make this multiplication of the reciprocal of this, so 2x minus 1 on top and 5 on the bottom. And what happens is these two factors cancel. And you also have, what, 5x over 5 left, which is x. And that's good news, isn't it? We have verified that f of g of x equals x. Does that mean that we're done? We can say they're inverses? No, we can say we're halfway there. Now we have to show that g of f of x also gets x. All right? So what I'd like for you to do is, for just a take-home, quick, easy quiz grade, is I want you to verify the other way. Okay? You verify on your own. On a separate sheet of paper, show with these two functions that g of f of x equals x. Turn it in at the beginning of class next time. All right? I'm not going to go through it. So we've now shown both ways, yes? We get x both ways? All right. So let's do the domain. How are we going to determine the domain? Yeah. Yeah, let's just do what we've been doing like last class, you know? Let's do what happens when we do this. X goes through g first, right? The g function was 4x minus 3 over 2 minus x. And then that answer, which is 4x minus 3 over 2 minus x, goes through the f function. And we already know what that comes out to be. X, right? But I'm going to write down underneath here what the f function was. It was 2x plus 3 over x plus 4. Yeah? So what are the domain restrictions going that direction? Like from x to here, what do we have here? X can't be 2, right? X cannot be 2, because if I plug 2 in here, I get division by 0. So x cannot be 2 here. That I'm doing by inspection, just by looking. I could set the denominator equal to 0, right? 2 minus x equals 0, and then solve for x. But I think it's easier just look and see. Now, what about this? This is the tricky one.
So it just can't be one.
This right here cannot be what? -4, right? But it's not x, it's actually everything that's getting plugged in, right? This is the part that's getting plugged in? So what I need to say to myself is 4x minus 3 over 2 minus x cannot be equal to -4. Understand? The output of G cannot screw up F. And to screw up F, this would have to be -4. So the output of G cannot be equal to -4 or else it's over. Yeah? So what I'll do is I'll figure out when that happens. So I'm going to have to take this right here, and I'm actually going to have to solve that equation. Whatever that answer is, I want to yank it out of my answers. So I'm going to have to do that over here. So when does this happen? When does 4x minus 3 over 2 minus x equal -4? So how would you solve this equation? Multiply both sides by the LCD. Multiply both sides by 2 minus x. That allows me to clear the fraction, doesn't it? I'm working with an equation now. The left side is 4x minus 3 equals the right side, -8 plus 4. So distribute. Can you solve that for x? How about, no, wait, hold on. Is that right? Plus? Yes? What do you get? What if I subtract 4x from both sides? What am I left with? -3 equals -8? What does that mean? What does that mean? What did it ever mean when we solved an equation, we got something ridiculous like this? No solution. That there's no solution. That's right. That means that the output of G will never equal -4, because you get an absurd answer here. You get that in order for these two to be equal, you would need -3 to equal -8. And that's not going to happen, ever. So when G is sitting here and it's like spitting out stuff, right? It's never going to spit out -4. Exactly. That's what's happening. So your only domain restriction is what? X cannot be equal to 2. So far. You got to check it the other way too, right? Okay, add that to your quiz. Check it the other way. Got it? Understand? So there's two things I want for the quiz next time. I want you to verify that g of f of x equals x, yes, which equals x, yes. So verify that g of f of x equals x, and then find any domain restrictions on g of f of x. So far what we have is x can't be 2, right? That's what we have so far. All right.
Find any restrictions.
Find any restrictions on g of f of x. Domain. Just find the domain of g of f of x, which is like what you did for homework last time. All right, so look, I know it's starting to feel like we're getting to the end of the semester, right? It's November, right? Snow's coming soon. But please understand that this course, the pace is going to be the same. If not, it's going to be a little faster, and the material is going to be a little more difficult. So don't get too complacent right now, all right? Just warning. All right. We have still 40 minutes. I still have a lot to do, all right? Let's just, that's a good point to just be like,
I really thought we were about to end the class.
no, sorry.
That was definitely an ending class.
It was.
Felt like it, right? It's now the halfway
We were
point.
talking about, stuff.
so far, if I give you a picture of a graph, right? You can tell me if it's a function. You can tell me whether or not it's one-to-one. If I give you two functions, you can actually check to see whether or not they're inverses. And you can actually find the domain restrictions. What you can't do yet is me give you a function and you come up with the inverse on your own. And that's what we need to be able to do also. All right? So let's take the example let's take something more simple. Let's start with something simple. I think that'll be good. So for this example, I want us to find the inverse of f of x equals 2x plus 1. Now we've already done this problem, right? And we showed a little while ago that the inverse of this function is x minus 1 over 2, right? I'm going to give you a set of steps, a procedure as to how to find the inverse of a function. Step 1, step 2, step 3, so on and so forth, all right? But before I give you the procedure, I just want you to get an idea of why the procedure is done, like why we do it. Okay, in our picture, do you agree that x gets spit out over here as f of x, right? And we've always looked at that as being the y value, correct? X goes in, y comes out. What we need to be able to do is find a function that takes y and sends it back to what? X. No, just listen to what I'm saying. We have a function, we know that it will turn x into y. We need to turn y back into x, right? So everything that was y now needs to become transformed back to x. Yeah? Okay. Now I'm going to give you the steps, and there's a step in there, and we do something, you may be like, why do we do that? Because visually, we need to take y back to x. So the first steps to find f inverse, all right? Here they are. This is a side note, like this is an example we're going to do, but these steps will apply all the time, all right? First step, rewrite your one-to-one function f of x with y notation. What do I mean here? Replace f of x with y. That's all I mean. But I said some things in here that are important. Rewrite your one-to-one function. So assuming that what you're looking at is a one-to-one function, which means it does have an inverse, right? Because there's no sense in trying to find an inverse of a function that doesn't have an inverse. So all we're going to do is look at the function, and we're going to replace the f of x with a y. All right? So I'm actually going to do the steps. Those steps, I'm going to do them over here on the side, and I'm going to give you the next step, and then do it, and then the next step, and do it. All right? So the first step would be to rewrite it like this.
How many steps are there?
Let me see. All right?
3. So I know how much space.
Replace. 1, 2,
39.
4.
4.
There's 4. But the fourth step's trivial, really. There's not a whole lot to do with step 4. All right, so the first step, you replace f of x with y. The next step, step 2, interchange x's and y's. What I mean by this is everywhere you see a y, put an x. Everywhere you see an x, put a y. So all your x's become y's, all your y's become x's. Why would I want to do that? Because that's what creates the loop backwards.